So, good afternoon, ladies and gentlemen, and I thank the organizers and also Henning that I have the opportunity to be here to share with you my view of the sulfur cycle that is related to the marine ecosystems. Today we see a remarkable decrease in Arctic summer sea extent at about 20% reduction since 1960. Currently, there is no clear explanation for the change in Arctic sea ice extent and thickness. And today, we don't know, we also don't know if the variability is mainly caused by man-made activity or if we see a record of natural variability. But how to separate man-made causes from natural causes? That is a challenge. If you want to challenge it, you need to select a region where human influences is least and natural variability is large. One such region is the Arctic, high Arctic region in summertime. You see on the left-hand picture the transport pattern of air in the summer high Arctic. And you can also see then that the air hardly touches pollution sources over land. A change of a change of the low-level cloud albedo or whiteness is one option to explain the change in sea ice. The high Arctic clouds, they are optically thin clouds, and that means that they are clouds with fewer but larger droplets than other clouds. So therefore, a small change in their droplet size and number is very important to the heat transfer to the ice and thus to sea ice extent and thickness. The cloud whiteness is in turn dependent on the number of particles available for uptake of water in sizes about larger than 100 nanometer diameter. And that is the effect that has been referred to during the earlier talks as the indirect aerosol climate effect. To sort these out, we need therefore the source of need to know the source of the summer high Arctic CCN, and that source need to be specified in order to understand the connection of cloud changes and changes of the sea ice. One idea that you can actually produce marine biological CCN is that if you have the component dimethyl sulfide or DMS from the ocean, that could generate CCN at the ice edge, which in turn could affect cloud whiteness and then could feed back on the phytoplankton community for changes in sea surface temperature. That idea came about within the framework of the claw hypothesis, an hypothesis named after its authors, Charlson, Lovelock, Andrea, and Warren. It postulates that there are two, it focuses on three conceptual ideas. The first one is an ocean temperature and phytoplankton production influenced by incoming solar flux at the ocean. And what that means is that you have the algal growth in the phytoplankton cells and that are producing the proteins. And in that process, you have a leakage of an acid called acrylic acid. And as a byproduct, you leak out the dimethylsulfonium propionate that is the precursor of DMS. Once once the cell has broken up by grazed from zooplankton, you will have an enzymatic transformation of DMSP into DMS aqueous phase. The second point concerns the CCM production linked to the availability of the gas DMS in the atmosphere, where you have a number of quite difficult both photochemical oxidation mechanisms in the gas phase, but also a gas to particulate phase conversion on pre-existing aerosol. The last point, number 3, concerns the number of cloud droplets and the cloud whiteness controlled by the CCN availability. Few CCN less bright clouds, many CCN, brighter clouds. CLAW became an historical milestone in the study of atmosphere and climate and led to thousands of articles and numerous field and laboratory experiments since 1987 when the paper was published in Nature. One such field effort came through the 4 subsequent high Arctic icebreaker expeditions launched in 1991, 96, 2001 and 2008, all with a mission to study CLAW, or the connection between CCN and the sulfur cycle. And here we see a panel on the right-hand side that goes from the bottom at the DMS in the water phase, DMS in the air phase, and the CCN in form of sulfur components from DMS, methane sulfonate, and sulfate from sulfuric acid. And you see they have a similar trend going from August to October with about 30% decrease per week. And then we also could see that the model ice zone and the waters nearest to the ice edge are the most biologically productive in terms of both biology then and DMS. And in the lower, whatever, how you do this, I don't know, the lower, this one, you can see there is a July to October, and you have a very strong seasonal production of DMS in the water along the ice edge. And here you see it's much higher levels than the world average. However, going in over the pack ice, you have first of all a delay in the peak of the season. It's more towards end of August, and you have 1 or more orders of magnitude less in concentration. So that means that it's actually the model ice zone that is feeding DMS in and sulfur in over the pack ice. That is also seen here when we look in the gas phase. We have let's see, here it was. We have DMS at the ice edge, moving in over the pack ice for 3-4 days and undergoing photochemical decline or oxidation. And at the same time, you are producing SO2 as you go in over the pack ice. So that is sort of a CLAW framework in a larger type of field experiment. So, and then finally we were able to put together the number concentration of the cloud condensation nuclei and related to the mass of sulfate then coming from DMS. The blue bar represent the other remote marine areas that is south of the high Arctic, and the pink squares and diamonds represent the high Arctic. And now, at least, I became very happy that, here CLAW is working. But be careful in science. Correlation do not prove causal relationship. So when we had the opportunity, the right technique to look at these particles, what they consisted of, we saw that we had a core of some aggregate, and outside we have the DMS gases condensed in the form of sulfuric acid. So this came as quite a surprise to us that this needs to be further investigated. So then we put the question, does DMS alone control the optical properties of the high Arctic clouds? And to find that out, of course, we tried to have a look inside the clouds. And here is a picture, an electron microscope picture from a cloud water sample. And we can see it's a Milky Way full of small particles in various sizes. And if you have a close-up, the particles looks like this. And you can also see the deposition areas or where water had been sitting just to form a good CCN. We also performed advanced liquid chromatography coupled with highly selective sensitive tandem mass spectrometry, LC-MS. And then we revealed a family of sugars, pentoses, dexohexoses, and hexose sugars. In parallel, we did some biological testing, and this picture shows immunostated particles collected in the cloud water with an antibody specific towards the Melisseria arctica community from the surface microlayer, which means that what we found in the cloud water came from the uppermost level, uppermost centimeter or millimeter of the ocean surface, the open water in between the ice flows. That is called the surface microlayer. We also could conclude that these particles are called marine gels, and they are produced when algae and bacteria synthesize energy from inorganic nutrients. And here you can see how a particle comes up from the ocean through a bursting of bubbles at the air-sea interface. We also know what the purpose of a marine gel is. It's proposed to act as a cryoprotectant and regulate osmosis. So freezing differences, melting and freezing different conditions, and also to regulate the salt conditions when the ice melts. We also combined these findings with detailed simulations, and we could, because of the marine gels consist of polysaccharide networks with interbridged with calcium ions and attached proteins, peptides, and amino acids, they turn out to be very, very good CCNs. So I said in the beginning that the source of the summer high Arctic CCNs needs to be specified. And now, after having a look into the cloud water, I of course say, oh wow, we found the source of the particles that the clouds are formed on. But you always have to be set back and review your new knowledge. So then another question, we can turn it around and now ask this question: is the gel theory of marine CCN coupled to the marine sulfur cycle? And on the left-hand side now, I show a size distribution of a number of particles. I show a size of particle diameter, and you see what typical particles in over the pack ice could look like. And then if we focus on the size, because in aerosol science, size is very important, in the sizes that makes up the most numbers of the CCNs, you find the gel particle in itself in a bacteria, you find the gel particles surrounded by sulfuric droplets, and you find the gel particle inside the stomach of this ammonium sulfate bisulfate particle. So from this you learn that there is a gel particle always as a core, and then you have the sulfur DMS chemistry as a growing material surrounding this gel particle. So now we can conclude that the number of CCN that are forming the number of the cloud droplets actually comes from the surface microlayer in between the ice flows or at the marginal ice zone. So if we are concerned with the whiteness or brightness or albedo of the clouds in over the pack ice, we need to know more of the biological processes that actually forms the sugars that are emitted from the surface ocean. So instead of looking at the claw type schematics, I put my schematics of how we can look for climate feedbacks in over the pack ice involving microbiology, biological processes, marine biological processes in the upper ocean, and the emission of particles from those processes. So having come this far, it's time to ask the question, is there a biological control on the formation of cloud droplets over the pack ice area? And I tend today to say yes. Does DMS control the optical properties of the high Arctic clouds? I say no, because it's not controlling the number population of the cloud condensation nuclei. Will biological activity and production of CCN increase or decrease with melting of the ice? Because that was the question I raised in the beginning. To be continued, because we don't know enough, even after 25 years of investigations in over the pack ice with the icebreaker expeditions. And that I'm looking forward to the summer of 2018, where the next expedition on the same topic will be launched. Moving outside the Arctic, so one can address another question: what are the connections between marine gel emissions and future environmental change, not only in the polar regions but also in the open ocean? And much of those studies have been focused on sea salt emissions over the years, but now an emerging picture is developing, that people starting also to find these marine gels with various direct or indirect methods. So I think there is much more to learn about the 70% of the Earth's surface covered by oceans and the role of marine gels in cloud formation. But for the Arctic studies, I think we can conclude today that it is demonstrated occurrence of polysaccharides or sugars promotes CCN activation. Promoting CCN activation suggests that marine gels could potentially become important for cloud droplet activation, not only over the inner summer Arctic, but also at lower latitudes. So that's for the studies of the Arctic, and as both Henning and I, we are working at the Department of Meteorology, so I thought we connect back to one very important person working or starting the Department of Meteorology, and connects back then via myself, Henning, Bert Bolin, and then Rossby. And Carl Gustav Arvid Rossby was a Swedish meteorologist who was the first to explain the large-scale motions of Earth's atmosphere today called the Rossby waves. But at that time, I think most scientists were lucky or unlucky, I don't know, but they were pioneers. They built on not known things at all, and they could be in all areas at the same time. And I happened a month or so ago to find in a folder at the department a paper notice from the 22nd of October 1956. And I translated what it was said in that article. It says, the project concerns the surface film that may be present in calm weather over large areas in the Atlantic and the Pacific Oceans. It's guessed that the film consists of fats, proteins, and other organic compounds. One is seeking answers to questions such as, to what extent is the film transported up into the air? By foaming, they suggested. Will the film change rainwater composition? Does it slow down evaporation? And does it affect the size of the raindrops? So, if I had known this, what they proposed 60 years ago, maybe we had stepped faster in the Arctic region. But they are absolutely independent investigations and suggestions. I just also want to turn back to claw. What happened to claw? But I think our findings in the Arctic has disproved claw, at least disproved claw. And we had a special issue in environmental chemistry in 2007 that was followed up in Nature in 2011, looking at a more wider picture, not only focusing on the Arctic. So today I think we say goodbye to claw, but remember to keep on the activity that claw has actually given us in the field of sulfur and ocean, cloud and climate. I know, Henning, that you are fond of poetry or poems, so I thought I'm getting now to the final phase of my talk. So maybe I could give you my view of the Arctic. One realizes in the end how mercifully the sun shines on the summer Arctic, this most desolate land of the earth. It is here where the sun has chosen to stand watch day and night to preserve the rest of our world and life itself. So by this, I thank all the members of the High Arctic Expeditions, and I also thank Henning for taking me on as a PhD student and later being a very good colleague and mentor in my work. Also important with, what has been so great with Henning is not only that we have shared research, but we also shared the other parts in life, family, cooking, bird watching. He has taught me everything I know about birds. Thank you, Henning.
Thank you very much, Carolina, for that fantastic scientific detective story of what's really going on up there. That's a really good example of how careful observation can really draw some insights into how some of these systems work. And a good example of feedbacks in the Earth system. Biology is really important on this planet, as we know. Anyway, let's have a few questions. The question was the story from 1956 from Dagens Nyheter, I think it was. What was produced from that work back then?
Yeah. To my knowledge, I haven't seen anything. So it's totally hidden in the darkness. So that's why I became so surprised finding this little article. Have you, Henning? No.
It was Rossby who said it, wasn't it?
Yeah, and in Uppsala. What is his name? Uppsala. Erik Eriksson. Erik Eriksson and Rossby.
Okay, any other questions? Well, I have one then. And just, if you look at this feedback mechanism up in the Arctic very simply, the first thing you would say is, if you're having a retreat of summertime, Arctic sea ice has been measured over the past several decades, you would expect more surface water to be, well, more surface water is exposed. You would, on the first order estimate, think you'd probably have more activity, biological activity, which would give you more of these gels. More cloud condensation nuclei, and you get a negative feedback with more clouds, which would then slow the warming trend. Is there any evidence that actually happens?
No. It isn't evident, it has started to look for changes in biological activity. And there you can see clear changes in how the ice retreats and you move the eutrophic zone along with the ice edge, and you get further in over the pack ice, you get more an ice edge bloom situation with the seasonality as you have at the model ice zone. So indeed, there have been changes, in the biology that have been observed. But if that is related to the emission of the gels, that is not seen. That's still to be investigated.
Mary.
So I'll guess. So increased sea surface temperature, if it is increasing up there, higher metabolic rate, more polysaccharides, more gels, more particles.
More particles.
Yeah,
okay, that's what
I'll repeat the question first. And Mary's saying as sea surface temperatures rise, you should accelerate the biological system so that you eventually get more CCN up in the atmosphere above the sea. And is that reasonable?
Yeah, that's reasonable, and that is the first-hand thinking that should happen. But you go to some extent with this, because eventually the ice is going away. And with the ice goes also the ice algae that usually starts the phytoplankton bloom in the surface waters. With the ice goes also the stratification that is very essential for getting a bloom at all. And so there are complications, and today we don't know when we turn the Arctic pack ice region into an ordinary open sea.
The question there is about the timing of these two effects, the retreat of the sea ice, which is late summer, autumn at a maximum, and the phytoplankton blooms, which may be mismatched. And just a general comment, we see this now in a lot of biological systems where timing between parts of the system is now a bit out of sync. Is that happening up here?
Yeah, and luckily, I wouldn't say luckily, but that the gels are benefiting from post-bloom conditions and also from heterotrophic processes. So that will tune in or time your what you described. Yeah. But much more to learn, but it's fascinating how these biological processes is tuned in to even master the cloud formation and surface radiation balance together with the eyes. It's fascinating.